Hi everyone, in this video we're going to talk about atomic theories, their developments. So let's start. Okay, let's start with the atomic models. The first one, Dalton's atomic model. Now before Dalton's atomic model, there are some laws of fundamental laws of chemistry that were developed by Antoine Lavoisier and Joseph Proust. Now let's remember what were they. The first one is law of conservation of mass. In fact, this is the beginning of the modern chemistry. This is the getting out of alchemy. So that's why Lavoisier is known as the father of the chemistry. Now the second one belongs to Joseph Proust, and this is already, law of constant proportions. So in the light of these fundamental laws of chemistry, Dalton's just announced his atomic model, and what he said is, elements are made of extremely small particles called atoms, and those particles cannot be formed or destroyed by chemical reactions. So he defined an atom like a billiard board like this, all fill in. The second one, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements are going to be different from each other. So we do not accept this statement nowadays because we talk about some kind of atoms called isotopes. Isotopes have the same number of protons, but they differ in their mass number. So this is not true for today. The third one, atoms of different elements combine in simple whole number ratios to form chemical compounds. If two elements can be combined to form a number of possible compounds, now what I mean is like nitrogen monoxide or the nitrogen monoxide. Another example can be ammonia and hydrogen. So you see they have this same type of atoms, nitrogen and hydrogen here, but they are in their atomic ratios. So if the two elements can be combined to form a number of possible compounds, then the ratios of the masses of the second element, which combine with the fixed mass of the first element, will be ratios of small whole numbers. Now, these long sentences, in fact, refers to the third fundamental law of chemistry, which is law of multiple proportions. And finally, what he stated is a chemical change involves rearrangement of atoms. So when two atoms are changed by places, they are told to be as chemical change. Okay, now comes the subatomic particles. Now after the electricity is developed, lots of experiments are made on electricity. So one of them, which Michael Faraday carried out, is known as the electrolysis. Now at those times they were talking about the static electricity. During the static electricity, there is no change in the chemical composition of the substance, but there's no change in the physical look of the substance. So they concluded that during this electricity, there is no atoms to be changed places, but the other particles, there should be some subatomic particles. So what Michael Faraday proved, in fact, that there are subatomic particles of the atom. So the Dalton's atomic theory is not correct. So he proved the existence of subatomic particles, and he stated that the quantity of current, or let's say that the quantity of charge necessary to deposit a given weight of an element is always equal to a constant or multiple of this constant. So for example, if you use 4 ampere of some current, if you have 4 grams of copper, when you just double that current, when you make it as 8 ampere, in this case this means you're going to have 8 grams of copper. So there's going to be direct ratio between the amount of metal deposited and amount of current passed through the system. And what quantitatively he found is the amount of electrical charge, that sentence, which produces 1.180 milligrams of silver is 1 coulomb. Okay, now that they told that there are some subatomic particles, so what are they? What are those subatomic particles? The first one is, in fact, they just started to talk on about electrons, because electricity is dependent on the electrons, so they try to deal with the electrons. The man who just give a suggestion about the charge and the name of the electron is Mr. Stoney. After him, Crookes carried out an experiment with his tube known as the Crookes tube. So this is the Crookes tube, this one. The name of this English physicist is William Crookes. He examined the behavior of a gas with electricity in a vacuum tube, not directly vacuum, but there is only 0.01 atm hydrogen gas in it. Okay, now that the existence of the electron is proved, here comes the calculation of mass and the charge of the electron. And those studies belongs to J.J. Thomson and Robert Millikan. We're going to start with the J.J. Thomson. Okay, now here's the scientist who calculated charge over mass ratio of an electron. And what he used is, he used electrical field and also some kind of a magnetic field in order to calculate the deflection amount of the electrons on a fluorescent covered surface. So he saw that deflection is reversely proportional to the mass of the particle used, and it's directly proportional to magnitude of the electrical field or the magnetic field. Okay, now this experiment seen on this slide belongs to Robert Andrews Millikan. Okay, what he did is he calculated charge of one electron. During this experiment, he used oil drops and he just pulverized these oil drops into real small particles. So why he used oil drops? Because oil drops can really be easily electrified. When some electrons are hang on in the air, they capture these electrons and they can be negatively charged. By the help of the oil drops and some electrical field and UV lights, he calculated the charge of one electron. Okay, now comes the discovery of proton. According to the previous discoveries, Thomson developed an atomic model which is called plum pudding model. Where the electrons are dispersed in atom randomly, what he suggested is there should be some positive particles that have the same number with electrons. So this is what we call as the plum pudding model of Thomson. So Ernest Rutherford believed in Thomson's atomic model, and he decided to prove that Thomson's atomic model is right. So he set up an experiment like this, which is known as the gold foil experiment. And the other name, in fact, this is alpha scattering experiment. During this experiment, he sent some alpha particles here, and he said that if the atom is homogeneous like the Thomson set, most of the rays should just get off this gold foil like this, or most of them should be maybe deflected like this. But during his experiment, he saw that most of the, probably 99% of the alpha particles just get through the gold foil, but only few of them like this deflected. So he said that the atom is not homogeneous like the Thomson set. Most of the place of the atom is empty, and there is a kind of place called nucleus, and all the protons are located in this nucleus. Okay, before Rutherford, in fact, Eugen Goldstein again used the Crookes tube. With the porous cathode plate to work on positive rays. Now remember, the other name for electrons used in the old times were cathode rays, because the rays were coming out from the cathode to anode. So we can say that the old name for the electrons are cathode ray, and these are the positive rays here in this case, because Goldstein used this Crookes tube not to prove the existence of electron, but prove the positive particles that are found in the atom. Finally, discovery of neutron. After some studies, the scientists agreed on that the mass of an atom is larger than that of the total mass of proton and electron. And Rutherford proposed that there should be some other neutral particles in the atom. So in order to prove that neutral particles, James Chadwick carried an experiment using, again in this case, a beryllium foil, and he said that there is higher mass than that of proton in the nucleus, and also he concluded that those particles have no charge and they should be named as neutron. Okay, now this is the last model before quantum atomic model, Bohr's atomic model. Now Bohr used quantum theory, Max Planck's quantum theory, in order to identify his model. According to his model, electrons can be only found on spherical orbits that have specific distance from nucleus. The orbits are named as K, L, M, N, or they can be numerized as 1, 2, 3, 4. So if you like to draw the Bohr's atomic model, in the center we have the nucleus, and around the nucleus we have the orbits, and on those orbits we have the electrons. So this is the first energy level, which has the lowest energy, and this is named as the K shell also. And this is the second one, which is named as the L shell. There is a specific amount of energy for every orbit, in fact for every electron. An electron wants to be at the lowest energy level, this is important, where it's stable, and this level is called ground state. So if you give some amount of energy to electron can jump up to higher energy levels, and that energy level is called excited state. An electron at excited state is, in fact, very unstable. It likes to go back to its original place. It can be the first energy level, the second one. When it goes back to its original place, ground state, it gives some kind of a ray out. This is called emission of a ray. Sometimes you can see this ray as a yellow light, blue light. It depends on the wavelength. Sometimes you cannot see this ray. It can be a gamma ray, or it can be ultraviolet ray. It depends on the type of the frequency and the wavelength of this ray. Energy for an electron at any energy level can be found with a formula. En is equal to minus 8 times z square over n square, where z is the proton number, which is known as the atomic number or the nuclear charge, and n is the energy level. So if you like to find the energy difference between two levels, you can apply this formula. Delta E is equal to A times 1 over n inner energy level square minus n outer energy level square. So this formula is used only for hydrogen. If you just like to find the energy difference between two levels for another atom, in this case you have to add some z square here. Please do not forget. Now this graphic indicates the spectrum lines and energy transition of hydrogen atoms. Now what is important about this figure is, for example, if you have an electron in this energy level, the first one, you excite it to this third energy level, it goes back to the first one again. Now all the let's say the electrons coming back to first one just indicates Lyman series. If it comes back to second one, it indicates the visible series. Now why we call it as the visible series? Because we can see these light as the colors. This means that it has a wavelength between 318 nanometers and 760 nanometers. These ones, bracket, Paschen and P fonts, these are IR rays, meaning infrared rays. These ones have low energy. If you have Lyman series, it has the ultraviolet rays, it is going to have high energies. Remember, high energy means low wavelength, and low energy means high wavelength. Okay, finally, if you like to summarize what we have said, let's start. The first atomic model belongs to Dalton. Now, secondly comes Faraday, who gives us an explanation about the existence of the subatomic particles. Then comes the William Crookes. He has a proof of existence of electron. Then Thomson, J.J. Thomson. He calculated the charge over mass ratio of electron. Also, he stated the plum pudding model of atom. Fifth one, Robert Andrews Millikan. Millikan. He calculated the charge of an electron. We can talk about Goldstein. He had the existence of the proof of the existence of the positive rays. We have Chadwick. Chadwick had the existence of neutrons, experiment for the existence of neutron. We have Rutherford, who carried out the alpha scattering experiment known as the gold foil experiment also. He is the man who firstly told that there should be nucleus in the atom, so his atomic model is known as atomic model with nucleus. Then finally we have Bohr's atomic model. He talked about the orbits. In the next video we're going to look at the quantum atomic model, starting with the quantum numbers.